A stuntman drives off a cliff traveling horizontally at 10 meters per second. He lands 3 seconds later. The first thing we'd like to do is sketch his motion diagram using position dots at 0, 1, 2, and 3 seconds. Well, let's go ahead and draw a cliff with some unknown height. And then we can draw the position dots. At t equals 0, put that right there. That's the position of the car, and it's traveling with a velocity that is purely horizontal. So we can draw the velocity arrow, velocity vector, something like that. Now, as I try to figure out what is going to happen, what I can do is I can think about what happens during free fall. What happens is the horizontal motion and the vertical motion is independent. So it's probably worth reminding ourselves of some of the basic concepts about free fall. Concepts. During free fall, we have first of all, we have kinematics. Kinematics, which is the mathematics of motion during constant acceleration. And we can also write the fact that we have free fall. And some numbers and some equations will correspond to those two facts. In fact, we can go ahead and write this down. Let's just list some of the equations that we know about. The kinematic equations are things that look like this. The position, let's say in the x direction, is equal to the initial position plus the initial velocity in that direction times time plus 1/2 ax t squared, so there's a velocity and an acceleration to consider. And likewise, velocity evolves in time as well. Vx is v naught x plus ax t, and the same equations hold in the y direction. So we can write those down. Y is equal to y naught plus v naught y t. So these equations look very much the same as the x equations. We just swap x for y. Vy equal to v naught y plus ay t. And there's a third equation you could write down as well. Importantly, during free fall, we have this very useful fact, which is that ax is equal to 0. There's no acceleration in the horizontal direction, which means that its velocity in the horizontal direction stays constant. On the other hand, the acceleration in the y direction is always equal to g pointing down. And so the way that we write that typically is to write this as minus g, where typically g is set equal to 9.8 or 9.81 or 9.80 meters per second squared on Earth. Okay. Now this is assuming that we have set things up so that y points up and x points this way. Anyway, that said, what should happen is that the motion of this stuntman in the car should be such that its velocity stays constant in the horizontal direction, which would mean that his horizontal position might look something like this over time, at 1 second, at 2 seconds, at 3 seconds. I'm drawing them as open circles just to get a sense of where they will be. The vertical position will evolve according to this free fall. And so if the object was not moving at all and it was just simply dropped straight down, it would start there at the top, and after 1 second it might be here, after 2 seconds it might be here, and at 3 seconds it'll be at the ground. In any case, we can start to then get a sense of what the position dots should look like. It should be, because this is free fall with some initial horizontal velocity, after 1 second it's here, after 2 seconds it's here, and after 3 seconds it's here. And so the rough shape of this path should look something like this. It should actually be a parabola. And the velocity arrow, the velocity is always pointing tangent to the curve, and so the velocity should look something like this, then something like this, and then something like this. Now, as a Just to simplify, to make things look a little bit nicer, I've pre-drawn one, which I will display for you here. Okay. We wanted to determine how far from the base of the cliff the car lands, and we'll also determine the height of the cliff. Well, what we've just established is that because the x acceleration is 0, that implies that the x position is just x naught plus v naught x t. And that's it. That last term is 0 because there's no acceleration. Because we're interested in what happens at 3 seconds, we can simply put in the initial position. Well, if we use clever coordinates so that the base of the cliff is at 0, this is the x direction, then we can choose our initial condition, initial coordinate, to be 0. That's a choice that we're allowed to make. The x velocity is unchanging and remains 10 meters per second. The time is 3 seconds, and so the final position should be 30. Notice the meters per second times seconds gives us units of meters. And so this position here where the car lands should be 30 meters. Lastly, what is the height of the cliff? This process of figuring this out should look very much the same. Because AY is equal to minus G, we can then figure out what our given that we have an equation that looks like this. Y is equal to Y naught plus V naught Y times T plus 1/2 AY T squared. We can simply evaluate this. When it lands, it has a final Y position of 0. Where it started was the initial height, which we can call h. It started off with 0 velocity in the y direction because that velocity was pointing purely horizontally. So this is 0 times t. And then we'll add to that 1/2 minus g and t squared. And so you notice I haven't really plugged in any numbers yet. I want to rearrange this and solve for h. 1/2 g t squared would be the height. Now I can plug in the numbers. We have 1/2 9.80 meters per second squared. The time is 3.0 seconds. That is squared. That should give me h. Notice that when I multiply this out, I not only get a number, I get 44.1, but what I have is meters divided by seconds squared times seconds squared. The seconds squareds cancel, and so my final answer is 44.1 meters for the height. And so we can now take a look at our picture, the final motion diagram.